Hello and welcome to lecture 45 of analog integrated circuit design. So far we have discussed negative feedback amplifiers in great detail, many kinds of feedback amplifiers including fully differential amplifiers, how to design them, how to simulate them and so on. Now we will move on to another kind of negative feedback block which works in a way similar to the negative feedback amplifier, but is very different in function. It is a device to multiply frequencies. Okay. Just like an amplifier amplifies an input voltage, this frequency multiplier or the phase lock loop will take a given frequency and give a multiple of that frequency at its output. Now this is an extremely important and useful block. It is used in all kinds of circuits including digital circuits. Basically it generates periodic waveforms with possibly varying frequency. Now even digital circuits need a periodic clock, so it is used over there. It is used for generating carriers for a radio where you need a number of carriers so that you can generate the modulation over them. Okay. So in general wherever you need a frequency reference you will need a source of periodic signals and this serves as the source. Now what we will do is to synthesize this block in a manner similar to how we got the negative feedback amplifier, and we will analyze it and evaluate the shortcomings if there are any and then overcome them, and that will finally lead us to a very popular topology of the phase lock loop. Now let us take our prototype voltage amplifier. What did we do? We took the input voltage, compared it with a fraction of the output voltage, okay. If this is V naught, this will be some V naught by K, and integrated the difference to drive the output. Okay. This implements V naught equals KVI for constant inputs Vi. Okay. And eventually when the circuit reaches steady state, V naught by K will be equal to Vi, the input to the integrator will be 0 and V naught will be K times Vi. Okay. Now let us say we need to make a frequency multiplier, okay, whose output frequency will be some n times the input frequency. I will call the input frequency as reference frequency because that is the common terminology that is used, and of course we will assume that the input frequency itself is constant. Okay. We can do it in an analogous manner. Let us say we know what the input frequency is, okay. We compare that to a fraction of the output frequency, that is, let us say this is the output frequency and here we get a fraction of that F out by N, and what we should do is based on the frequency difference Fe, we should integrate the difference and drive the output. Okay. So this is a frequency multiplier and it is very easy to see that when Fref is a constant, steady state is reached when Fe is 0, that is the input to the integrator is 0 and F out by N equals Fref. In other words, F out will be equal to N times Fref. Okay. Now there are some details that we have to fill in. First of all, in a voltage amplifier things were easy. Okay. Our electrical signals are in the form of voltages or sometimes currents, and we either compare the voltages and drive the output with the integral of the voltage difference, or we take the difference between currents and drive the output with the integral of the current difference. Those things are possible, but here again we have electrical signals which are voltages or currents and they are periodic with a certain frequency. But what we need to compare according to the diagram that we have come up with is a comparison of frequencies, not comparison of voltages. Okay. So, the voltage will have a certain frequency and we need to be able to compare the frequencies. Okay. We will see how to do that shortly, but before that essentially we will be dealing with periodic signals whose period can be changed slowly and so on. Okay. For instance, the output frequency could be changing. Now, strictly speaking, such a waveform is not periodic at all, but we need to be able to handle those signals. So, first we will look at definition of frequency and phase in a more general way than for a constant frequency sinusoid. Okay. Now, let us start with a periodic signal that everybody is familiar with. Let me just take cos 2 pi f naught t. We know that this is a periodic signal and this could be some voltage with a peak value V p. Okay. Now, we will break it down into the basic periodic function, that is cos theta. Let me remove that V p from here onwards. Cos theta, this is a function that is periodic in theta with a period 2 pi, that is cos theta plus n times 2 pi for any integer n will be the same as cos theta. Okay. So, this is something we all know. Now, if we substitute theta equals 2 pi f naught t, the function that we get cos 2 pi f naught t will be periodic in t as well with a period 1 over f naught. Okay. So, this is a signal that is periodic in t. So, what we will do is we will consider this form of the signal which is by definition periodic in theta, and then define theta as a function of time. Okay. This looks like a roundabout way of doing things, but it is very useful as we will see. So, let me now plot this theta with t when theta equals 2 pi f naught t. Obviously, this describes a ramp whose slope is given by 2 pi f naught. Okay. Now, the function cos theta is periodic with a period 2 pi. So, on the y axis I will mark integer multiples of 2 pi and so on. Now, I will look at the times at which the ramp crosses these thresholds, okay, crosses 2 pi, 4 pi, 6 pi, etc. Now, because this ramp of course is a straight line, these intervals will be equal to each other and they will be equal to t naught, which is the reciprocal of f naught. Okay. So, this is pretty clear. So, essentially we can define a periodic signal in time as signal that is periodic in time. We say that it has a phase that is a ramp, okay, that is an ideal ramp. The phase changes linearly with time, okay, and this phase is the phase of a periodic function such as cos theta. So, the resulting function will be periodic in time. Okay. Now, we can see what happens if we deviate from this. First of all, let me take a simple modification. I will add a constant offset phi naught. Okay. So, what happens in that case? I will simply get a ramp that is shifted by phi naught. The slope is still the same as before, it is 2 pi f naught. Okay. Here I am drawing the new phase theta with respect to time, and then I look at the points at which the times at which the new ramp crosses 2 pi. Okay. And it is clear that these intervals are also equal to each other and also equal to T naught, which is 1 over f naught. Okay. So, a constant phase offset does not take away the periodicity of the signal, and this is pretty obvious as well, because we know that instead of cos 2 pi f naught t, if we have sin 2 pi f naught t, that is like adding a phase of minus 90 degrees, and that is periodic as well. Okay. Next, let us take a different case where I have this offset as well as some part that varies with time, and I will assume for now that this has a 0 average. Okay. That is, any average value is captured in this constant offset, and this phi of t itself has a 0 average. Okay. In this case, what happens? Of course, it depends on phi of t, but let me plot it for some arbitrary case that I will consider. So, let us say it deviates like that. Okay. So, you have the ramp plus the offset plus also some time varying quantity. Now, if you now look at the time instants at which the new phase crosses integer multiples of 2 pi, so let me pull all of these things down here. It is clear now that these intervals are not necessarily equal to each other. Okay. So, depending on the type of variation in phi of t, you will have a certain variation in the period of the signal. Okay. So, basically this representation is very useful to describe signals which are deviating from ideal periodicity. Okay. Ideally, the phase of a signal should be a ramp, that is, if you have the phase to be an ideal ramp, a straight line with time, then the resulting signal will be periodic in time. Okay. Now, if you have the phase of a periodic function, but the phase is not exactly a ramp, let us say it is a ramp plus some time varying quantity, then the successive periods of this function will not be equal to each other, it is aperiodic. Okay. Now, it turns out that anything that you generate will not be exactly periodic, there will be all kinds of deviation from ideal periodicity. Okay. This could be due to systematic variations, or it could be due to random variations, such as we encounter offset and noise in voltage and current domains. We can have this kind of deviations in the phase domain. Okay. And this becomes extremely important in the generation of periodic signals, and also in the analysis of systems which generate those signals. Okay. So, that is why we discuss this. So, the bottom line is that we start with a periodic function which is periodic in theta with a period 2 pi, and to describe a signal that is periodic or almost periodic in time, what we do is we represent this theta as consisting of 3 parts in general. this is the ramp and it represents the average slope. That is, these two parts will have a slope of 0 and this part represents the average slope. So, this f naught is really the average frequency, okay, because the signal is not exactly periodic and the average period is T naught. Okay. And there will be deviations from this and the average deviation is captured in this phi naught. Okay. And finally, the time varying part of the phase excluding the ramp itself is time varying, but we know that a periodic signal has a phase which is a ramp. So, that is excluded from this. Excluding that, all of the time varying parts are included in this phi of t. Okay. So, to specify a signal that is periodic in time with some deviations, all we have to specify are these numbers. In fact, for the first number you only have to specify the frequency f naught. Okay. So, you have three parts to it. One is the frequency f naught, the other one is the average phase shift phi naught and the rest is the time varying phase shift phi of t. Okay. So, of these f naught and phi naught are trivial and many times you end up working only with this time varying part which is phi of t. Okay. And by knowing the nature of phi of t, we can also deduce the deviations from periodicity. Okay. Again, the reason we do use this representation is we are only interested in if the signal is periodic or not. Okay. Now, I have started with cos of theta, but it does not have to be a cosine function, it can be any other function. Okay. Many times you could have a square wave or some other wave shape. The shape is not what is important. What is important in these systems which generate frequencies is whether the signal is periodic or not. Okay. So, instead of cos theta, we could have any other function, okay, p of theta, which is also periodic in theta with a period 2 pi. Okay. So, then only the wave shape will be changed, but the periodicity will be the same as long as these theta values we plug in here are the same. Just to give you an example, let me draw two waveforms here. In this particular case, I have drawn 4 periods of the sine wave with a high frequency and 4 more periods with a lower frequency. Okay. And this is a sinusoid. And I could have a square wave which behaves exactly in the same way, that is the frequency shifts to a lower value after 4 cycles. Okay. Or I could have a pulse train whose frequency again varies in a similar fashion. Okay. It shifts from a higher frequency to a lower frequency. Okay. Now, in all these cases it is only the basic shape that has changed. Okay. So, this is by the way plotted versus time. In all these cases the basic shape with respect to theta is what is different. Okay. So, the first one has a sinusoidal shape, the second one has a square shape, and the third one has some narrow pulse shape. Okay. And in this with respect to theta, all of them have a period of 2 pi. Okay. What is different is this function p that is periodic. Now, there may be applications, in fact there are applications where the shape of the waveform is important, but it is not important for the generating these periodic signals. Okay. We know that we can turn a square wave into a sine wave by putting it through a filter, or turn a sine wave into a square wave by putting it through a high gain amplifier which has some limiting. Okay. So, we will not now worry about the waveforms, and most of the discussion in the generation of periodic signals, that is for the phase lock loop, will be in the phase domain. Okay. And this you would have commonly seen if you refer to any textbooks. The main reason is that we are only interested in whether the signals are periodic or not, and not really what the shape of the signal is. Okay. So, in all these cases if you plot this theta versus time, what happens is up to this point it has a higher slope, and after that it has a lower slope. Okay. What I meant to draw here is a constant frequency and a lower constant frequency. So, that means that phase is ramping up to this point, and again after that it also ramps up, but with a much lower slope. Okay. So, this is the general definition of phase of a signal. Okay. And there is also, from this we can define the generalized frequency. This, by the way, I emphasize, is the average frequency, and the frequency that I am going to calculate is known as the instantaneous frequency f, and this is given by 1 over 2 pi time derivative of theta, okay, which you can see is f naught plus time derivative of phi of t. Okay. Now, if the time varying part is 0, if phi of t is 0, the instantaneous frequency equals f naught. Okay. Now, this makes sense. What that is saying is, if the signal is exactly periodic, okay, possibly with some extra constant phase shifts, average frequency will be the same as the instantaneous frequency. Okay. If the phase has time varying component in it, then the instantaneous frequency will be different from the average frequency, and the average frequency will be equal to f naught. Okay. So, clearly this also will have an average value of 0. Okay. So, earlier I said that anything that is ramping up is captured here, the constant offset is captured here, and the time varying part with 0 average is captured here. Similarly, the average frequency is captured in this one, and the time variations on top of that are captured in that one, okay, which has an average of 0. So, it is important to get familiar and comfortable with this. You would have come across this in communication systems if you have taken such courses. When you study modulation and so on, notion of generalized frequency is very important in frequency modulation and phase modulation. Okay. and it is also important for us for the study of phase lock loops. Now, one of the confusing things in this may be the use of the term frequency. It will be used for many things. Okay. For instance, let me write out the expression for the phase again. And this can be called frequency, and what is meant here is of course the average frequency, and the instantaneous frequency, this could also be called as frequency. Okay. So, this is another thing. Now, also because we have phi of t that is time varying, it can be varying at a certain frequency. So, we will also use the term frequency in connection with that. So, that is used like that, that is this phi of t itself could be a sinusoid at some frequency. That frequency has absolutely nothing to do with this f naught. It could be coincidentally related to f naught, but it in general has nothing to do with it, and it has its own frequency. Okay. Similarly, we will not deal with instantaneous frequency too much, we will deal with this instantaneous phase. But it is possible to do all the analysis with the instantaneous frequency, and then this time varying part of the frequency can have its own frequency. Okay. Again, there is nothing to be confused about, they are just different signals that we are talking about. Okay. As long as you understand that f naught means average frequency, this f of t means instantaneous frequency, and these time varying parts can have their own frequency, everything should be fine. Okay. And it is also quite common to sometimes take the Fourier transform of phi of t and plot it obviously on some frequency axis, and it could have any kind of shape. Okay. That is basically phi of f. So, this frequency axis which denotes the frequency of this phi of f, that is this phi of f denotes the content of phi of t at different frequencies. So, there is yet another frequency here, okay, which is basically the x axis of the spectrum of phi of t. Okay. So, the same term frequency is used for many things. So, just go through the definitions and be clear about exactly what frequency we are talking about in what context. Usually it will be quite clear, it only takes a little bit of getting used to initially. Okay. Now, with that introduction to general notions of phase and frequency, we can go ahead and try to realize the frequency multiplier that I earlier described. So, what do we need here? I said that I have the frequency of the input signal and frequency of the feedback signal, which is 1 over n times the frequency of the output signal. We need to have this integrator which will control the output frequency f out, and we need to have this divider which will take the output frequency and divide it by a factor of n. Okay. Now, as I mentioned earlier, the input will not be a frequency, but obviously it will be a signal of a certain frequency. Okay. Let me call it Vref, and I will denote the input by a sinusoid of frequency f ref. As I emphasized earlier, the waveform does not have to be a sinusoid, but it can be any periodic signal p with a period of 2 pi. Okay. So, that is what is applied here, and we measure the frequency of that. If we do that, we will obviously get f ref, okay, and that has to be compared to the output will be a signal at the output frequency. Let me say cos 2 pi f out t plus some phase offset phi out. Okay. So, in general the phase offsets can be different. Here also I will show it as some phi ref. Okay. So, now what the frequency divider will do is to give a signal whose frequency is 1 over n times the output frequency, and it turns out this phase offset will also be 1 over n times the phase of the output. We will see quickly, we will see soon how this comes about, and we have to measure the frequency of this one. Okay, and compare the two. So, at this point we will be getting f out by n. So, what I am trying to describe here is that we will have signals, that is voltages or currents with a certain frequency. I will usually take the example of voltages. The input will be a voltage with a frequency f ref, the output will be a voltage again with a frequency f out. The frequency divider will take the output voltage and generate another voltage whose frequency is f out by n. Okay. Now, the two things we wanted to compare to compute the error, the two things we wanted to take the difference of are the frequency f ref and the frequency f out by n. Okay. So, from the voltage signals V ref and the feedback signal at the output of the frequency divider, we need to measure the frequency of those signals and get f ref and f out by n, and these two quantities we compare, that is we take the difference and integrate the difference to control the output frequency. Okay. So, here I should be careful with how I specify this. I will show this box disconnected. What it is meant here is that the integrated frequency error is not this voltage, it is the frequency of that voltage. Okay. Again, this simply follows an exact analogy with the voltage amplifier. The only confusing parts can be that we are dealing with voltages which have certain frequency, but we have to do our operations on the frequencies of the signals, not on the voltages themselves. That is why I am doing this. Okay. So, we need to be able to control the output frequency, that is we need a block whose frequency can be electrically controlled. If it can be done, then we can drive it with the integral of the frequency difference, that is drive it with this signal and control the output frequency. Now, it turns out that to control the output frequency f out, there is a block that is available which is known as a voltage controlled oscillator. Now, you know that oscillators are autonomous blocks which generate periodic signals. Okay. Now, what we are trying to do here is to control the frequency of periodic signals using negative feedback. Now, there are also certain kinds of oscillators whose output frequency will depend on some electrical variable such as voltage or current. So, you could call them voltage controlled oscillators and current controlled oscillators. I will call them voltage controlled oscillators or VCOs. So, what it does is to receive an input voltage Vc and give a periodic signal, which as usual I will denote with a cosine at a frequency f out, and there will be some arbitrary phase shift phi out. Okay. Now, how is this f out related to Vc? In general, it will be something non-linear, but we can very usefully model it as f out being some constant of proportionality times Vc plus some f naught, that is some offset frequency, and this is known as the free running frequency. Okay. This is nothing but the frequency at which the oscillator will oscillate if Vc is 0. Okay. That is pretty obvious from this expression. If Vc is 0, f out will be equal to f naught, and this kVco is the gain of the VCO. This voltage controlled oscillator is usually abbreviated to a VCO, and this is VCO gain, and it is measured in hertz per volts, that is for unit change in the control voltage, how much does the output change, okay, output frequency change. So, that is given by this. So, this voltage controlled oscillator can be used as a block that electrically controls the output frequency. Okay. So, what do we do now? We can generate the output using a voltage controlled oscillator, and the control voltage of the oscillator must be related to the integral of the frequency difference. Okay. So, once again if you walk through this, what happens is the system will reach steady state when the input to the integrator is 0, then Vc will be a constant, and if Vc is a constant, the output frequency will be some constant. So, we will have constant frequencies everywhere and steady state is reached, and under that condition Fe equals 0, that means that f out by n equals f ref, or f out equals n times f ref. Okay. So, all we have done is to split the forward path into two parts, one which is a tool for controlling the output frequency electrically, and the other one which is to provide this control as a integral of the error between the input and feedback frequencies. Okay. So, this is the model of the VCO. Okay. Now, one important thing here is that again the VCO output can be written as cos or any other periodic function with a period 2 pi of theta of t. Let me call it theta VCO, or maybe theta out of t, where theta out is given by 2 pi f naught t plus 2 pi k VCO integral Vc of t dt. Okay. And this will be, if Vc happens to be a constant, 2 pi f naught plus k VCO times Vc times t. Okay. What I am trying to emphasize here is that if Vc is time varying, you cannot use the second relationship. It is not f naught plus k VCO Vc of t times t, it is the integral of Vc of t dt. Okay. Now, if Vc happens to be a constant, then simply the frequency is shifted by k VCO times Vc, and if Vc is 0, then we will have the output frequency to be the free running frequency f naught. Okay. So, this is the phase model of the VCO, which we will be using continuously from here onwards. Okay. After a while, after we complete the design of this block, we will model everything in terms of the phases of signals, and this is the model we have to use for the VCO. Okay. Now, this block diagram is fine, except we do not yet know how to do this measurement of frequency and so on. Okay. We will quickly see how to do that. This VCO, it can be made, you may have heard about the VCO, and later in this course we will see some examples of how to make the voltage controlled oscillator. So, we will assume that this can be made. And how do we make this frequency divider? That is, if you feed in a voltage, whose frequency is f out, then the output must have a frequency of f out by n. Okay. Now, there may be many ways of doing this, but the most convenient when n is an integer is to use a digital counter. Okay. A digital counter, you know that a divide by 2 counter, if the input is like that, the output will be 1 for one cycle and 0 for the next cycle, 1 for one cycle and 0 for the next cycle, and so on. Okay. And clearly you see that the output has half the frequency or twice the time period of the input waveform. Okay. Now, we will only be considering the case when this n is an integer. So, this frequency divider will be realized using digital counters. Okay. Now, the one other thing is here I showed cos, that is sinusoidal waveforms at the input and the output of a divider, and you may be wondering how a digital circuit will operate with such waveforms. As I said, I will keep showing the functions as cosine, just so that I have to show something, but it can be any other waveform, okay, any other wave shape which has the same period of 2 pi. Okay. So, obviously, if you have a digital counter, most of the time it operates with waveforms that are more like a square wave than like a sine wave. Okay. But without loss of generality, I can write cosine everywhere. So, we now know how to make the frequency divider as well. What is left is the rest of these blocks. Okay. Let us consider this part of it. What is happening here is we measure the frequency of this signal, we measure the frequency of the other signal, take the difference between frequencies and integrate the difference to get the control voltage. Okay. Okay. And we integrate the difference. Now, I can equivalently write this as measurement of frequency, and I can pull this integral into both of these branches, this branch and that one. Okay. I will pull the integral into both of those paths. Okay. Now, what we are doing is we are taking the input signal, measuring the frequency, integrating it, taking the feedback signal from the frequency divider, measuring its frequency and integrating it and taking the difference. Okay. What is this entire block doing? It is taking the frequency and integrating it, which is basically measuring the phase of the input. Okay. Because what is phase after all? I said the instantaneous frequency is 1 over 2 pi times the time derivative of the phase, and if I invert this I will get the phase to be 2 pi times integral of the instantaneous frequency. Okay. So, all this is doing is to measure the phase of the input signal. This is measuring the phase of the feedback signal, the output of the counter. Okay. So, the quantity that we get here is nothing but the difference between the phase of the reference signal and the phase of the feedback signal. Okay. I will denote this signal by the subscript FB. So, what we really need to do is we do not have to measure the frequency and so on, we do not yet know how to do that, but what we need to do is to simply measure the phase difference between these two waveforms, that is measure the phase difference between the reference signal or the input signal and the output of the frequency divider. Okay. So, what do we get in that case? We need some block that measures the phase difference between these two, and this is nothing but the control voltage Vc of the voltage controlled oscillator. Okay. Because we have combined this entire thing, measuring frequency and integrating the difference, which was giving us the control voltage Vc, into this single block which measures the phase difference. Okay. And it is measuring the phase difference between the output of the frequency divider okay. At the output we would have cos 2 pi f out t plus phi out, and here we would have cos 2 pi f out t plus phi out, the whole thing divided by n. Okay. So, this is the frequency divider or the counter, and here this Vc will be related to the phase difference between these two signals, which is basically some constant of the phase detector Kpd times the phase difference, where theta ref is this much and theta fb is that much. Okay. And for the system to be in steady state, this ramp part has to be 0, that is f ref has to be equal to f out by n. This we had come up with using a different kind of reasoning. In fact, this is the objective of our design, to make f out equals to n times f ref. So, this part will be 0 and this part will be something that is related to Vc and some parameters of the circuit. Okay. So, this entire block with this phase detector, the block that takes the phase difference is known as the phase detector, a voltage controlled oscillator and a frequency divider. This is known as a phase locked loop or PLL, okay, and it is a very widely used block, and by changing n you can also change the output frequency from the same input, okay. And in fact, that is the mode in which the phase lock loop is used very often. It has many other uses, but one of the main uses is for what is known as frequency synthesizers, okay. By changing the value of n, the output frequency will be n times f ref, n times the reference frequency. So, by changing the value of n, the output frequency can be changed, okay. And you know that you can make digital counters with programmable division modulus. So, by programming the modulus you can change the output frequency, okay. So, that is the basic phase lock loop. In the next few classes we will look at exactly how it behaves, how to realize the different blocks of this phase lock loop and so on. Thank you. I will see you in the next lecture.